Hi. So I think this is the second time I've presented this one, but last time it wasn't quite working. Want to say, huge thanks to Chris for helping me out with this. Couldn't have done without your help. So last month I brought in a little humanoid robot that I'd made, and this month I'm actually finally showing it off. The finalized version of it. This is a Plen robot. This is from Japan. But the thing is that none of this, the only thing I actually bought from them was the board. Everything from the servos to the 3D printed parts, I either had to manufacture my own, or in cases of getting the joints working, I had to laser cut all of the joints and everything. The purpose of this little biped robot is that it's a multi-purpose humanoid. Turn it on, turn the servos. Basically, as soon as I turn this on, everything's going to slam into motion. All right. And so I was really interested in biped robots for a very long time. I've been very interested in how they walk, the kinematics for them. So I started off with looking at different kinds of designs that are available, different kinds of processes, and so that got me interested in what Japan was doing. So I was looking at different, I'm a huge fan of Robo 1, which is a contest that they have for bipedal robots. When I found out that I could actually source parts to build my own humanoid robot for even less money than what they were going for, then I got really interested. So the robot I showed last month actually was actually stolen from me. So I had to actually, I had it on 4th of July weekend, and someone stole it from my bag, and so I think they don't know what it exactly is. So this took a lengthy process of me. Of me actually being able to rebuild everything in a matter of several days. So as soon as I got the second Arduino-based board with the Bluetooth, I was able to basically source all the servos, find everything again, and then get it to a significantly better working state. So right now everything is on an open loop right now. It's controlled from my phone on this small app right here, but I can control all of his movements. I can control the way he walks around, or it can walk around. I can control different actions with it. I can control, for instance, if I wanted to do something like have him pick up a box. Hoping that this isn't the right size for it. See if I can pick it up. All right. So I might need to adjust a bit, but all right. Sorry for picking it up. But all right. Okay. So it's not perfect, but I can still have him walk around a little bit like this. So the main purpose of this is that I want to eventually start doing more development on it. I have a Pixie Cam, and I'm very interested in doing more computer vision related work. Basically, I've been taking it out to coffee shops in San Jose and getting more people interested in biped robots. It's very weird bringing a biped robot because people don't know what exactly it is, but it's for them it's really acute and appealing. So that's the main draw of why I take it out. So anyway, you can ask me more questions. I modified basically every single part that was 3D printed I had to modify. So if anyone wants the files, I'm more than willing to share with the community. So, yeah.
Hello everyone, my name is Gabriel. And this is my friend Nikki. So we work on this robot together with two other friends who couldn't make it today. And Nikki's gonna explain to you the general idea of this robot and the hardware.
Hi. First of all, I want to mention that me and Gabriel worked on this for a senior project in undergrad. So what we're trying to do is create essentially two Roombas. So the current Roomba, it's able to map its own environment and go its path in that way. But in this project, we wanted to have two Roombas that communicate their location data to each other so that they don't traverse the same path. So let me briefly explain the hardware that we use. So we have a Raspberry Pi, a motor driver, 4 DC motors, and one ultrasonic sensor, which is what we're using. The other 3 we didn't want to use because it was not really necessary. So we stuck with one, and 2 IR sensors as well. We want to improve this in the future, but for now this is what we have. There are also 2 wheel encoders. So our mapping is basically done through kind of a grid layout. So with reference to its starting location, it tries to determine its next location after it moves. So the wheel encoder is there to make sure that the wheels are aligned when it moves. So every time it moves 30 centimeters, for example, it marks a location on the map. And so that it doesn't move out of the path that it's supposed to go to, the wheel encoders are there to realign the wheels and make sure that it traverses the entire room in a neat fashion. So I'll give it to Gabriel to explain more about the mapping.
So we had 4 ultrasonics here. We have 4 ultrasonics, but we ended up not using 3 of them because it causes a lot of problems. So what we do is we use the distance we get from these ultrasonic sensors, and then we draw the map. We sort of like draw part of the map from each robot into a square grid, 30 centimeter each specifically, if I remember. And then both robot updates the map to a REST API that we host on a server, and then they feed it back to the robot. So it constantly updates the map. Like each grid on the map has a status of is it traveled, is it detected? It's all booleans, and is it an obstacle, right? So then it will decide each robot will try to go to the next closest grid using an A-star AI algorithm to decide which path to go to and like the path itself, and also that way it will optimize cleaning a single floor space with minimum overlapping paths with each other. And yeah, there's some inaccuracies within, like, because it's in a fixed grid system, of course, right? You can go slightly forward and slightly to the left or to the right with the rotations. But then it always, it has a fallback program, which is a spontaneous navigation, so it just spontaneously avoids obstacles. So it also works with dynamic obstacle if you have a cat at home. We intend to have a vacuum cleaner on it, and we didn't manage to do that yet. And because we have to change the whole hardware scheme, as you see, we got a lot of cables and a lot of pieces here, and so we're planning to do that later. And we're also considering like a lot of improvement. Number one is the grid system. Oh, the first problem is the ultrasonic is very inaccurate, so we're considering LiDAR or even cameras for using computer vision. And also, yeah, the whole grid system mapping is very prone to inaccuracies. And yeah, we would like to actually install a vacuum cleaner, and we would like to see like how like more machine learning stuff could increase the performance, like predicting the map or something like that, right? So, but that's what we have right now. Thank you for listening, and we're open to questions.
Do they have to start next to each other, or how do they find their location?
Yeah. So we were planning to make it somehow know the location of each other, but like we were short on time at that point, so we just make it start next to each other, so it knows its position beside relative to each other at the start, so it draws the map the same way.
So you're doing this like all the how you know where you are is entirely based on the wheel odometry, and it doesn't have any like other sensors for localization.
Yeah, basically. So it's kind of like trusting that this works. So that was the biggest issue in our robot. The wheel encoder is not very accurate, first of all. Second of all, I'm using only 2 wheel encoders when I'm supposed to be using 4, because there's 4 motors. But that can't be done because 2 of the motors are tied to each other. So if I send out a signal to move forward, 2 wheels will be moving together. So the wheel encoder idea is all tied with the way the whole thing is designed. So what we're trying to see is that if we improve the whole design and still stick with the wheel encoder, will the mapping still be accurate? If not, which is a high possibility, we might need to turn to a completely different methodology. Yeah.
Is the architecture extendable to like 3 or 4 or N robots?
Yes.
What processor are you using?
We're just using 2 Raspberry Pis.
Where are the IR sensors? You said,
Yeah, it's right
One's
here.
up front, yeah.
so can you detect the edge of the table?
Not really well. We could,
Yeah,
but
not
it's
well.
not really well.
You should think about making that modification, then you can join the challenge next time.
Yeah. We're thinking about that.
Right? Okay, thank you.
Thank you.
So this is an update on humanoid robot that I've been building. It looks better than CAD. So there's the CAD. So before I had one leg, so now I've got one leg, and I managed to join them together, I think, in a good way. So I'll show you that. So here's a leg. Just set this here. Okay. So zoom in. Basically, they're joined together with this beam in the middle, and then I'm working on the body now. So you can see I got the body. My plan is to put a Arduino type of thing right in the chest, and then I'm going to use a serial servo controller from Pololu, which is going to be up here on the head. So I guess the progress that I made was that I'm pretty happy with the way the legs got joined together. I got the battery in here. I moved the legs a little bit further apart because they were kind of hitting together. I 3D printed this yellow beam, so I actually started using my 3D printer to iterate a little bit faster. So now I joined this body holds the arm servos. So my question now is to how to bolt it into the beam in a solid way, so that if you have a bunch of torque on the arm when it falls down, you don't just rip the body off. So right now I think it is not that great, because it would just have too much moment. It would rip off the plastic beam. I think in the back I can actually peg it all the way across the bottom, and then that could take up a lot of that torque. So that's my plan. I also think I could make the beam metal instead of plastic. That's kind of where it is right now. And then I plan to have 2 switches right here for on and off, and then I have to cram one more battery in there for the microcontroller. And then I think I'm going to make a little backpack to have the remote control kind of stuff. And yeah, but I feel pretty good that at least I got a good idea of how to go forward. And that's it. Not yet, no. Good.
Chris, did you make all the metal parts as well?
Yeah, so I got the CAD done at 4 o'clock, and then I ran to my garage and I made this in like 3 hours. Yeah! Nothing like a robot meeting. Can you do my meeting? Yes?
What iteration is the body on?
The body iteration, like 3, 4. This is like my 4th one. I had one and I cut it up and I tried that and that didn't work. So then I went to this. Actually, and I did 3D printed one that didn't work, so didn't bring that one. Yeah. I'm just trying to start to be able to iterate faster, feel faster. So I was kind of bummed because like a lot of stuff didn't work, and then I just said, well, at least you're getting there. So I think I'm pretty happy with this. Where it's going to go, we'll see. All right, thanks.
My name is Doug Bacon. My robot, I'm calling it BerryBot. The objective is to pick stuff off the ground. It has a stereo camera. on the back. It has its own lighting. It's just 2 degrees of freedom. I haven't managed, I still want to add the third one. The third one would be to actually move the shoulder. Right now the shoulder's fixed. The arm is a trash picker that's actually is pivoting on the steering pin of the wagon on the bottom. So it's just I took a door hinge for 1 degree of freedom, and then the pin is the other degree of freedom. But my main objective with this, I'll get it going in a second. I don't. Hopefully it'll work. It hasn't been out in the backyard before. But my main objective is to experiment with behavior strategies. I have a hierarchical state mechanism that uses Lua scripts. I don't know if anybody's played with Lua, but Lua is nice because it integrates very easily with C++. You can call into it and call out of it.
What kind of scripts?
Lua.
Oh, right.
But, anyway, let me see if I can load a script and see if I can get it going.
Right. You think the monitor is big enough?
Almost. So that shows. So what it's doing now with the paths is that it's computing the paths. There's a PC inside of it, and it's computing each path segment as a chain of waypoints, and then it's queuing that to an Arduino, and there's an Arduino that's actually sending pulses out to the stepper motor. So, So I'm gonna put it all on the line here and see if I can pick up a berry. All right.
Oh. All right. Nothing up the sleeve. I don't think I could pick it up with that gripper.
Yeah, it's not 100%. So what's involved here is that there's a stereo camera that has its own coordinate frame, and then there's an arm that has this coordinate frame. So the arm is kind of orthogonal to the ground, and then the camera's at an angle. So there's a couple issues there. Move it, Mark. Sure. Oh, okay, I see. Is that better?
Yeah, camera's not very.
Watch out, you run over the berry. Don't move the cart. You see it?
I have more. Yeah, so they're plastic berries. So I'm going to load one of my Lua scripts here.
Can't really see anything.
The camera's not very helpful.
That's better. Better look at the monitor.
And then if I find the berry, let's see if it finds it. Okay, it's finding a bunch of other stuff here. So basically, it's just using blob, and then it's transforming. It's using the stereo equations to figure out where the berry is from the blobs. But I don't know why I have the yeah, I'm sorry, it's not going to run because I have the color threshold for picking up too much other stuff. So.
You had a different color for the 4?
Yeah, I don't. So it's the gain of the camera is. I usually have it outside, so the gain of the camera is a little bit different. That's something I have to work on.
Is it because they cut it?
Maybe. Let's see here.
Can you approximate? See?
I'm sorry I can't give you a good demo right now, so.
It's all right. You got,
That's all I
come
can
back next month.
Next time.
Come back next month.